Hello, everyone, and welcome to the webinar today in the AI for Net Zero webinar series. I'm Heiko Balster from the University of Leicester, and I'm going to introduce our speaker for today, Professor Clare McCabe from Heriot-Watt University, in a moment. First of all, I would just like to say that the webinar series is designed to bring together experts, innovators, and enthusiasts from both the artificial intelligence and sustainability domains. And with an overarching goal to accelerate progress towards net zero targets, the series aims to engage and inform communities about the groundbreaking research and developments at the intersection of AI and sustainability. So Clare McCabe is a bicentennial professor at Heriot-Watt University, where she focuses on molecular modeling and simulation to understand biological systems, fluids, and nanomaterials. She is recognized for her contributions to carbon capture technologies, aiming to advance net zero goals. And previously, she was a professor at Vanderbilt University. Clare has received prestigious fellowships from the American Association for the Advancement of Science, American Institute of Chemical Engineers, the American Institute of Medical and Biological Engineering, and the Royal Society of Chemistry. And she is involved in the ECO-AI project, exploring AI-enabled carbon dioxide capture with integrated solvent and process design. I'll hand over to you, Clare.
Thank you. So you see my slides, yes? I'll assume the silence is a yes.
Yes, thank you.
Okay. So yes, thank you for having me talk today on some of the work that we're doing on the ECO-AI project. You'll see that I've added a little "and MoSDeF" to the title of the project, and we'll see why that is shortly. So our role in the ECO-AI project is to focus on the carbon capture component, excuse me, and in particular the capture of carbon dioxide from flue gas. And so you can see here, hopefully you can see my mouse, but I'm not sure if you can. But you can see here we have a typical chemical process flow sheet for the process. And so you have the flue gas coming into the bottom of this absorber column here, where it will contact with a liquid solvent that will absorb the CO2 so that we can release the clean gas from the process. And we then need to remove the carbon dioxide from that solvent in the desorber process so that we can capture the carbon dioxide and we can recycle the solvent so it can be used again. So this is a fairly, a well-established process. The problem is that it's very energy intensive. So it requires about 20 to 30% of the energy that's generated to recover the solvent, which is known as the parasitic energy cost, and is something that we'd like to overcome. Can we reduce this percentage by using an alternative solvent? We've chosen to focus on the solvent because there is a very strong link between the solvent properties and process performance. So for example, the heat of regeneration and the heat capacity tells us how much energy we're going to need to regenerate the solvent. We need to know the viscosity. So if you have a solvent that has a very high carbon dioxide absorption capacity, so it can load a lot of carbon dioxide, but in the loaded state, if it has a very high viscosity, then it's not going to be a very practical solvent to use. And we also, of course, need to know the solubility. How much CO2 can the solvent hold? And also what temperatures and what conditions do we need to then release the CO2 from the solvent? So we proposed in this project to look at 4 different classes of solvents, which I've listed here. So from the aqueous amine solutions, which are currently used, but looking at new amines that haven't been studied yet, through to ionic liquids and deep eutectic solvents. And the issue here is, if we want to develop, which is the goal, an AI-driven solvent screening pipeline so that we can improve this process and discover new solvents for the CO2 capture. The problem is that this is a very vast chemical space. And before we can even start to ask questions like, what kind of AI model should we be using? What should we be doing? We have a problem in that we have very limited data availability. So we need data in order to optimize the process. So we need the solubility of carbon dioxide in this wide array of solvents, some of which will have not yet been synthesized. We need viscosity data for both the neat solvent and the solvent when it's loaded with CO2. We need thermal properties. We need surface tensions. There's a lot of data that we need, and there's a lot of missing data. Excuse me. There's also the problem that experimental data generally comes from multiple sources, and they tend to have differing degrees of reliability. So there's patchiness in the data. There's also often problems with not having data over a full, range of state conditions. Experimental groups typically tend to report a lot of data at room temperature and pressure, which leads you with holes when you're trying to really plan a process and look for data over a wide range of conditions. And so this has led really to an emerging trend of using computation to develop or derive pseudo-experimental data. The advantages of this is that we can generate large amounts of data. It could come at a high computational cost, but the data will be of a high consistency. It will be good data, for want of a better word. The disadvantage is that it is a prediction. So, no computational method is exact. So whatever data we use to develop our machine learning models, those machine learning models are only going to give us properties as good as what the simulation would have predicted. So we need to make sure that the models and the methods that we're using to generate this pseudo data are as reliable as possible. So what we really need to do is computational screening of soft matter systems. We need to be able to screen that large parameter space to get the properties that we need to optimize the process. But screening in soft matter is a hard process. You can contrast that with hard materials where essentially the atoms and the molecules are fixed, they're in lattice positions, and so it's much easier to calculate those properties because you know where the atoms and the molecules are. In soft matter, you have to actually do a calculation to determine what is the equilibrium structure before you can even think about calculating the properties. So for soft matter, if we want to go from the chemistry of the system, the state condition, to the properties, we have this fairly long process that we have to follow. And so before we go through that, let's just all make sure we're on the same page when we're talking about what it is we're doing when we need to do a molecular simulation. What do we need? So the term molecular simulation refers to a wide range of methods for connecting the way in which molecules interact with each other and their properties. We primarily do molecular dynamics simulations, which is just one particular flavor, where we're solving Newton's equations of motion to generate trajectories through time. So we're following the molecules as they move through time, and we then calculate the properties of interest from those trajectories. The important quantity is this energy, the potential energy here, which describes how the molecules, how the atoms within the molecules interact. And so this is what we often use the term force field, and it's just an empirical equation which tries to describe as best as possible the molecular interactions. So we have terms that describe the bond stretching, bond angle bending, torsional motion, and the non-bonded interactions, such as if you have two molecules and you're bringing them together, when do they start to attract each other and when do they repel each other? And so this is the force field, which is a very integral part to doing a molecular simulation. So the first thing we have to do once we've decided, what system it is that we want to simulate, we have to ask, do we have the force field? Do we have the parameters that will tell us how those atoms and the molecules are going to interact with each other? And if not, then we would often have to derive those parameters, sometimes from ab initio calculations, other times from fitting to experimental data. But if we have the parameters, then we can initialize the system. So we need an initial configuration. We need to take the chemistry that we're interested in and replicate it so that we have an initial configuration, be that a bulk system or a surface, whatever it is that you're trying to calculate the properties of. And then you need to equilibrate that. So you have to run the system for a period of time whereby it forgets that initial configuration, so that the properties you calculate are not dependent on where you started from. We then run the simulation for what we call a production run. So we run it for a relatively long time, nanoseconds. And And how long depends upon what properties we're trying to calculate and what system it is that we're studying. And then you do averaging on those trajectories so that you can finally get the properties. And so these are all the steps that are involved, and this is what led us to develop what we call the molecular simulation and design framework, so that we could do this computational screening efficiently, generate pseudo data, because while this looks on paper relatively simple, each of these arrows encapsulates a number of important steps. And very often when people publish their simulations, and even within a research group, when you are doing simulations, you don't write down every single thing that you do. And so it can make it very hard to reproduce this work. And so one of the goals of MoSDeF was not only to enable computational screening, but also to enable more reliable and reproducible data. So just to say a word about reproducibility, there's been a lot of talk about reproducibility in the literature, some high profile articles such as this one here in Nature, where they're talking about a reproducibility crisis in scientific research. And while the discussion is primarily focused around experimental research, the same is true of computational work. And the questions are asked, how do we make computational work and molecular simulations more reproducible? What are the best practices? And what's really clear from those discussions is that automation is essential. And that makes a lot of sense. If you think about, if you want to make something that's individual and bespoke, then it would typically be handmade. If you want to make something that's identical every single time, then you have an automated manufacturing process. So automation really is key to reproducibility in computational science. What else is also clear is that the code and the data must be made readily available, and we need to avoid GUIs and black boxes where you're hiding the data and the order of calculations. And so all of these things went into how we built MoSDeF. We built MoSDeF on the ideas that you should have automation, version control, open source software, and complete data dissemination. And so by doing this, we ensure that we do what we call true simulations that are transparent, so somebody else can come along and see exactly what we did. They're reproducible, people can reproduce what we did, they're usable by others, and they're extensible. So let's look at what do I mean when I talk about the MoSDeF tools. What are these tools? So MoSDeF is an open source Python stack. It's built on open source components, and there are 3 key tools under development in what we call the MoSDeF suite. MBuild is the first one, which is a hierarchical component-based toolkit for building our molecular systems. So taking the chemistry that we're interested in and building that up into that initial configuration that you need to run your simulation. And so we can do this in like a Lego brick fashion, where you start with small building blocks and get bigger and bigger. You can also do it by simply reading in a configuration using standard formats such as a PDB file. We then have FOIA, which is our atom typer. So this is how we apply the force field. And it is simulation engine agnostic. So it doesn't matter what simulation engine you're going to run the simulation in. Ultimately, you can use FOIA to take your initial configuration and apply the force field. And primarily we use the OPLS force field for those that are familiar with molecular simulation force fields. Once we have our initial configuration and we've parameterized it, we can then use GMSO, or the generalized molecular simulation object, to write out the configuration files, the input files that we need to run the simulation. Primarily, as I said, we focus on molecular dynamics simulations, but over the last 5 or so years, we've been working with a number of other research groups to expand the codes that we directly interface with MoSDeF, so that you can write out input files for all of these molecular simulation codes. As I think was mentioned in the introduction, I was in the US for 20 or so years, so this is predominantly a list of US universities. But we want to change that. Now we've moved over to this side of the Atlantic. Okay, so the last piece was something called Meta MDS, which was what we were designing to enable us to do the screening and manage all the data. But Sharon Glotz's group at the University of Michigan was essentially simultaneously developing something called SINYAC and SINYAC Flow. And so we actually used that tool with MoSDeF to do our computational screening. I should also say that there are a number of other open source utilities that we use, some of which are listed here. So if we go back to that scientific workflow that we need to use to do molecular simulation, how does MoSDeF impact this workflow? So obviously MBuild is going to enable us to take the chemistry and build our initial system. So build that initial configuration. FOIA will parameterize our system, and then using GMSO, we can write out syntactically correct files that we need to run the simulation in your favorite simulation engine, assuming it's one of the ones that we support, which is pretty broad these days. And then, as I said, we use Synyac and Synyac Flow to manage the whole workflow so that you can execute thousands of simulations in parallel. So Synyac enables you to, for example, loop over the chain length, loop over the chemistry, loop over state conditions, so that you can do the computational screening, and then manages all the data that you're going to generate as a result of those calculations. Now, just to give you an example of how we use MoSDeF, I wanted to talk about one project, and in particular this work that we've been doing on screening monolayer-based lubricants. We are using MoSDeF in the carbon capture project, but we haven't got to the point of publishing that yet. So since this is recorded, I didn't feel comfortable really, letting the cat out of the bag, as they say, and talking about the work before we've really dotted all the I's and crossed the T's. So I'm going to use this project to illustrate how we use MoSDeF and just come back to a few points on the Eco-AI project at the end. So this work is around designing lubricants that can be used for nano and micro electromechanical devices, or MEMS and NEMS. So these are basically miniature machines, and they have wide range of applications. They're used a lot, for example, the accelerometers in iPhones is one very common everyday example. But our advancements in fabrication have really outpaced our ability to lubricate these devices. Their small sizes, which is advantageous, poses challenges because you have very high surface area to volume ratios. And so that means that the surface forces dominate and you get stiction between the parts, which leads to wear and poor device longevity. So you need ways of lubricating these devices, because traditional lubricants that we would use in a car engine, for example, are just too viscous. Monolayer films have shown good promise, I guess is the word as use for lubricants in these systems, and in particular alkyl silane monolayers. And if you coat surfaces with these alkyl silane monolayers, the densely packed chains do reduce the surface energy, they protect the underlying surface from wear, and so they extend the life of the device. But the frictional properties that you get from these systems really vary with the composition of the film, the terminal group, the chain length, the density on the surface, etc. And we've done a number of empirical studies to try and understand this behavior. But what we wanted to do as we were starting to develop MoSDeF, we asked the question is, could we do a computational screening and use MoSDeF to analyze the structure property relationship so that we could understand the relationship between monolayer chemistry and tribology? How do we design a good lubricant film? So these are the simulations that we are looking at. We have two amorphous silica surfaces that we then coat with these alkyl silane chains. And here we have the surfaces capped, or the chains, sorry, capped with a CH3 group, but it's that cap that we're going to screen over. So we apply a constant normal load, and then for different normal loads, as you shear the system, you can calculate the frictional forces. So you can plot the frictional force as a function of the normal force, and then using a Manton's law of friction, from this data, you can get the adhesive force, which is really the force that you need to get the system moving. So how much force you need to exert to get the motion. And then the slope of the line here gives you the coefficient of friction. So basically the ongoing friction. So in this initial study, we looked at 16 different terminal group chemistries. So there's that CH3 group, and then we have 15 other chemistries that we studied. And we chose these to have a wider array of behavior. We didn't look at systems that we tried to think chemically what would give us a good lubricating surface. We wanted some that would be good and some that we would expect to be bad. And so you can see here's our setup. We have the silica surface, the alkyl silane chain, and then the terminal group. And we have this in what I call an AA situation, because you have the same monolayer on both the top and the bottom surfaces. Now, with this initial study, we did around 1,200 simulations, because we looked at the effective chain lengths. We have 5 different chain lengths. And so for every single one of those 16 terminal group chemistries, we did 5 chain lengths, 3 normal loads, and 5 different simulations, so that we, 5 replicas, so that we could get good statistics. And at the time, we thought that, 1,200 simulations was actually quite a lot. Turns out to be not so many, as you will see. But with MoSDeF, this is a relatively easy thing to do. You can design a workflow that is fully scriptable. It can be shared via GitHub. So that makes sure that we're applying the true principle. We are doing simulations that are transparent, they're reproducible, they're usable by others, and they're extensible by sharing our scripts and everything that we use when you publish the simulations, when you publish the work. So MoSDeF, we can use mbuild to construct our systems, Foya to atom type it, GMSO to then write out the files that we need so that we can run the simulations in GROMACS. We use MDTraj to analyze the trajectories. And then, as I said, Signac and Signac Flow to really manage the whole workspace and do the screening. So if we look at some results, the first results that we have is just looking at the effect of the terminal group. And this is actually for the longest chain, so for the C17 chain. I'm not going to show you all the other chain lengths, because basically the data is the same. We know from this work and from previous work that if you have longer chain lengths, you have a more cohesive film, and that does overall lead to lower frictional forces. So we're just going to concentrate on those longer chains. And so here what we're doing is just plotting the coefficient of friction and the adhesive force from the lowest value to the highest value. And before doing this study, intuitively, what we always thought is that if you had a terminal group that had a high adhesive force, it would also have a high coefficient of friction. So if you needed a high force to get the system moving, you'd expect there to be ongoing high forces during the movement. But you can see that that is completely not true. This group here that has the highest coefficient of friction actually has the lowest adhesive force. So that was somewhat counterintuitive to what we've been thinking. So we decided that we would do some more simulations and get some more data, because at this point we only have simulations for 16 systems. So we went back to our original data set, and instead of having that AA system where you had the same monolayer on both the top and the bottom surfaces, we now have AB systems. So we have one monolayer on the top surface and a different monolayer on the bottom surface. We're only focusing on one chain length this time, because we know that the longer chain lengths will give us better frictional properties. And again, we're looking at 3 normal loads and 5 replicas of each of the simulations, so that now we have 80, and we've added an additional 84 unique systems, so for a total of 100, and we're doing another 1,200 simulations. Excuse me. So if we plot those results, basically it's just a scatter graph of the adhesive force as a function of the coefficient of friction. The yellow symbols are the symbols where we had the AA, so we had the same monolayer on both the top and the bottom surface. And the blue symbols are where we have AB, so we have a different monolayer on the top to the bottom. And you can see in this region here, this is what we're interested in, because we are trying to minimize both the coefficient of friction and the adhesive force. That's what will give us a good tribological properties. And so that's shown in this figure on the right-hand side here. And these are those 7 chemistries. And you can see that there's a lot of the cyano group, so a lot of thin molecules. And if you look at this a little bit more carefully, what we start to see is that you tend to perhaps have one surface that is hydrophobic and one surface that is hydrophilic, presumably so that limits hydrogen bonding across the monolayers, which would drive up the frictional forces. But beyond that, we wanted to try and understand what molecular fingerprints, what properties should we be looking at in these terminal groups in order to design a good tribological film. So a film that has low coefficients of friction and low adhesive force. And so we turned to machine learning. And in particular, we used RDKit which is an open source cheminformatics package to assign molecular descriptors to each of the terminal groups. These descriptors essentially fit into 4 categories. So they characterize the size of the group, so the size of the terminal group, the shape, the complexity. So do we have branching, and the charge distribution? Do we have a polar group? Do we have hydrogen bonding possibilities, etc.? And so we then trained a random forest model to develop a machine learning model that would predict the coefficient of friction and the adhesive force, and also tell us which of these molecular fingerprints, which of these groups or descriptors contribute most to the tribological properties. And so what we found from this is that really the coefficient of friction appears to be most influenced by the molecular shape. We have all these strange sounding words here or groups here, and these descriptors basically all refer to the size, the shape of the group. And so what you see is that you get the lowest coefficient of friction when things are linear. So when you have what we call sp hybridization, so like that cyano group, this carbon with the triple bonding to the nitrogen, and they start to get higher as that group gets bigger. So as you go from thin molecules to planar molecules to bulky sp3 CH hybridization like the CH3 group. So it's clear that the coefficient of friction really is dominated by size, whereas the adhesive force is not particularly influenced by size. It is the charge distribution. You get low adhesion when you have terminal groups which have low polar surface area and do not have the ability to hydrogen bond. So this initial study was interesting. It did provide us with some molecular insights, namely that it's the shape that influences the coefficient of friction, and it's the polarity that determines adhesion. And while this information is useful, though, we really only looked at a very small portion of the design space. Ooh, I think I clicked in the wrong space there. Hopefully that's back. So we've only looked at a small portion of the design space. So using MoSDeF, we thought, well, we can generate a lot more data. So we can really try and tackle this and answer the question, what films would be good for having good tribological properties? What chemistry do we need for good tribological properties? But rather than add a lot more chemistry, we actually only added 3 new terminal groups. We decided to explore this idea of mixed monoliths, because what we saw from the previous 100 systems, that we got lower tribological properties, or better tribological properties, lower coefficients of friction than adhesive forces when we had mixed monoliths. So we're looking at systems now where we have the bottom monolayer can be a mixture of 2 different functional groups, A and B, and the top monolayer can be a 3rd functional group, C. And we're also looking at this in 2 different ratios, where we have a 50-50 mixture on the bottom monolayer and a 25-75 mixture. So now we've gone from 100 unique systems to 13,000 unique systems. We're only doing 3 replicates this time, but we're still doing those 3 normal forces for every single system, which gives us 120,000 simulations to manage. So we've gone from thinking that 1,200 simulations was a lot to now doing quite routinely 120,000 simulations. Yes, it took a while, but using MoSDeF and Signac, you can easily manage such a complex workflow. So if we look at the results, and again, this is just a scatter plot of the adhesive force as a function of the coefficient of friction, and it's this region in this red box down here that we're interested in, where we are minimizing both of those quantities. And if we look at, well, what chemistries are in those boxes, or in that box, then you see it's a lot of ternary systems. There's only one system where we have a binary system, where we have A, B, as opposed to A, B, C. And so again, that cyano group, the thin groups pop up a lot. But we've still only explored a fraction of the design space. As I said, we only added 3 different new chemistries. But now we have a lot of data. And so the logical next step was to develop machine learning models and to see if we could use those machine learning models to more efficiently look at that vast chemical space and tell us where we need to deploy our resources and do more detailed simulations. And so with the machine learning models, we wanted to do two things. We wanted to test the transferability, so how well the models could predict the tribological behavior of systems that weren't included in the test sets, and how much data we really did need. So here we're looking at the usual scatter plots, where you're looking at the predicted property in comparison to the simulated property to see how well the two agree, for both the coefficient of friction and the adhesive force. And we're looking for two different machine learning models. So A and B here at the top come from machine learning models trained on just that original 100 data points. So just a relatively small data set. And CD are from machine learning models trained on 1,000 data points, randomly sampled from the 50-50 train set. So we take those systems that had a 50-50 mixture of A, B on the bottom surface and C on the top, and choose 1,000 data points from there. And so there's a couple of things to note. First is we generally see more scatter in the prediction of the adhesive force, particularly in the higher adhesion regime, than we do for the coefficient of friction. But that's not particularly a concern, given that what we're interested in is identifying systems with low adhesion values. So quantitative agreement in the higher regime is not really required. But what's interesting is that while obviously the machine learning model trained on those 1,000 data points does do better, there's a better agreement between the simulated and the predicted behavior, the machine learning model trained on only 100 points is doing pretty well to say that this system contained no mixed monolayers. It was just pure top and pure bottom monolayers. We didn't have a mixed monolayer. And so this is very encouraging with the idea that these models are somewhat transferable, in that we can use it to perhaps do an initial screen and look at chemistries and systems that we haven't included in the training set. The other big question, as I said, was how much data do we really need? As I said, we had 13,000 unique data points now. And so we were able to ask the question of, how big of a training set do we really need to use in order to get accurate machine learning models? And so what we're looking at here is, if we ask the question, what are the top 30% predicted systems from the machine learning models, and how do they compare with the top 30% from the MD simulations? How much overlap is there in those two lists? And how does that overlap change as a function of the size of the training set? So you can see that as we go from relatively small training sets of 100 data points up to 1,000, we have a rapid increase in that overlap. So we're seeing more and more systems in the machine learning model top predictions in the MD top predictions. But what soon becomes very clear is that there's diminishing returns once you add more data beyond that initial 1,000 points. And so again, this is very encouraging, which it's telling us that we can do this combinatorial approach where we can perform a small set of relatively expensive MD simulations to train a baseline machine learning model that we can then use to explore the parameter space and identify where we should be deploying our resources to study more carefully, which chemistries we should be looking at. A caveat, though, is that obviously identifying a priori which systems we should simulate to get an appropriate training set can be challenging. And just one last example is, so now we have these machine learning models, let's look at some new chemistries. Let's look at other systems that we are missing. And so we looked at the ChemBL small molecule library, which has about 2 million compounds in it. We filtered out any molecules that had an atomic mass, a molecular weight basically of more than 100 atomic mass units, charge systems that can't be handled by RD kits, and metals. And that left us with about 200,000 unique systems. And so we screened those 200,000 systems for pure monolayers and AB monolayers. And this took about 24 hours, which is a huge turnaround compared to 24 hours for a single system when we're doing the MD simulations. And it did give us some new chemistries to look at. And so the question is with these new chemistries, would they give us better tribological properties than the best performing systems that we saw so far, which always involved the cyano group. And that's something that we haven't looked at yet, that we'd love some experimentalists to look at. So just in the last couple of minutes, I just wanted to finish off by coming back to the EKOAI project and how we're using MoSDeF and machine learning to tackle that solvent design problem. One of the properties that I mentioned that's important is viscosity, and viscosity is one of those expensive properties to calculate. It requires a large number of long simulations. And so we're trying to be more creative in how we design our machine learning models. And so we're using an approach called transfer learning, where we're doing a large amount of relatively cheap simulations, non-equilibrium molecular dynamics simulations. So we're calculating the viscosities, using that data to train a machine learning model that is then refined using a small amount of more accurate NEMD data. And this is working quite well. One of the things that we're looking at here, which is different from our previous work, is we're looking at the connectivity of the molecules. So when we were looking at those monolayer films, we only really cared about the chemistry of that terminal group. Here, it's not just the chemistry in the molecules that's interesting, but also the connectivity of those molecules, that is going to affect the viscosity. The other property that we're focusing on a lot is obviously the solubility in the phase equilibria, but here we're taking a slightly different approach. Instead of using molecular simulation to generate our pseudo experimental data, we're using theoretical approaches. In particular, we're looking at the SAF gamma me group contribution equation of state, which is developed by our collaborators at Imperial College, and also looking at COSMOS-SAC, which is a general activity coefficient model. And we're using these two approaches to, again, generate those pseudo data so that we can develop machine learning models to compute the VLE orders of magnitude faster than we could by just doing the calculations themselves, but also looking at, can we use the machine learning models to help us optimize parameters? We want to explore new solvents that haven't been studied. And so just like there's not experimental data for those parameters, there's not experimental data, sorry, for those molecules, there's often not parameters for those molecules. And so we want to try and use machine learning to help address that issue as well. So in conclusion, hopefully I've shown you that using the molecular simulation design framework, you can perform large-scale screening of soft matter systems. We've combined MoSDeF with a workflow management tool, in particular with Signac, and it can handle a very large number of systems. We've done more than 140,000 tribological simulations using MoSDeF and Signac. We've been able to then use that data to train machine learning models and shown that you can use, in the case of random forest that we used, you can use relatively small amounts of data to get good predictive models that can provide us with physical insight and can also be used to identify new areas of the chemical parameter space that we need to study. And MoSDeF itself is still an ongoing development. It's co-developed by myself now at Heriot-Watt with Peter Cummings, but also this was work that came from a group at Vanderbilt working with computer scientists and a number of other groups across the US. But we are always looking to expand the capabilities. It is available obviously on MoSDeF, so take a look, and if you're interested in working with us, let us know. And I think I'm out of time, so I will just leave my acknowledgement slide for a second or two there. Thank you.
Thank you so much, Professor Clare McCabe, for your really interesting presentation. We invite everybody who's watching to type their questions into the comments box online so we can read them out. While people are doing that, maybe I will open with the first question, and that is whether there are any benchmarks for assessing model-generated data in situations of not having enough observed data. How do you know that the model-generated data are any good, basically?
Yeah, so often, you will start with a class of molecules for which there are data. So you'll start with things for which you know the answer, and if you can validate on those systems, then you do have to take a bit of a leap of faith, but it's not too much of a leap of faith to say, well, if it works well for these systems, then it should work well for this. A lot of the work that we do, though, we do in collaboration with experimentalists. And so, we do that initial validation, we do some predictions, and then you come back full circle and you go back and say, well, these are some systems that we'd now like to look at. Did we get it right, and are they good systems? So it is, really it's a circle.
Thank you. We have more questions coming online, so yes, they will appear on screen, hopefully. So we have one question here. How can you effectively navigate the vast and potentially non-smooth design space in material science? What strategies can be employed to handle discontinuities, local optima, and high-dimensional parameter spaces using AI for materials design and discovery?
I mean, there's different approaches that you can take, and I think always, that's a very open-ended question. I think it was Ahmed. It's a very open-ended question, but I think it's always good to take a step back and just make sure that what you're getting makes sense, and use different approaches, use different methods to check that you're getting consistent results and not just putting all your eggs in one basket, as it were to say. And even, for example, with the tribological data that we've used, we have gone back and we've looked at other, not using random forest, looking at other approaches, and we get similar data, similar results.
Thank you. I'm just waiting for some other questions to be typed in.
Excuse me.
In the meantime, on a personal level, I would be interested in hearing your opinion, Claire, on how MoSDeF will actually help accelerate the transition to net zero for carbon capture and storage. So what do you gain by having this technology?
I mean, it certainly allows you to do large-scale simulations. As I mentioned, there is a real problem, not just in experiments, but in simulations, with being able to reproduce other people's work, and not just other people's work in the literature. We all start, when you start a new project, you typically will go to the literature or somebody else in the lab who's done something similar, and you make sure that you can reproduce that before you start to do something else. And you can spend a very long time just trying to get to that point that you were already at, get to the point of, well, this student could do this, so you should be able to do the same thing. And so it's really trying to overcome that barrier. If you can really document the provenance of the simulation, where did the parameters come from? What exact parameters were used? As people who do simulations will know, very often when you're looking, say, at the OPLS force field and you're trying to parameterize the system, you might have choices about which parameters to make, and people don't always say exactly what they did. And so that makes reproducibility very hard. And so if we're going to generate large amounts of data, pseudo data, so that we can train machine learning models, so that we can discover new materials that will help us, with carbon capture and storage, we need to be sure that the data, the simulations, the data is right. And with MoSDeF, someone else could come along, look at exactly what we did, make a few small tweaks, and rerun everything. They can reproduce everything, but also rerun everything and do, add their own flavor to that. So I think it will help with the data provenance and being sure that the models that we are developing are being trained on reliable data.
Thank you. And how scalable is the uptake of the technology, carbon capture and storage? Apologies for the drilling noise in the background. I've just started building works here. Anyway, carbon capture and storage as a technology, how scalable is that?
So I'm not sure I understand exactly what you mean.
So what I mean is carbon capture and storage requires some investment into creating facilities, and you need to somehow get the carbon out of the gases, basically. And how much can you scale this up? So could we not just take all our carbon emissions out of the atmosphere with this technology?
I'm not quite sure how to answer that. I mean, what we're focusing on is the solvents, and that is a vast. There's many solutions. There's a vast possibilities that we could look at, and we're just looking at one small part. But we think that the tools that we have will play an important role in that. And I look forward to maybe in a year's time actually being able to talk about some of the work that we've been done. It's a little daunting thinking that something's going to be recorded when, you know, for posterity and you haven't actually published it yet. So that's, you know, why we didn't get into a lot of the nitty-gritty about the carbon capture and storage work today.
Okay. So we have one more question. To what extent can transfer learning be effectively applied in materials design? And in what cases might we still need to build new machine learning models for each system?
I think there is certainly still space for new models. You know, so one of the limitations, which I think is what Ahmed is, I'm not sure if it's Ahmed, but what that's getting at is that, you know, so with the models that we built for the tribological properties, we were limited by by the bounds of the training data. So we were never going to find a system that the model would predict would have a better tribological performance than the one that the best performing one that we had. Now it can suggest new chemistries, and as I said, we could go off and test those new chemistries, and they might turn out to have better or worse behavior than we predict. But what we'd like to have is models that that can go beyond the bounds and can learn as we're developing the models. And we are looking at that in not just in the carbon capture and storage area, but also in another project, which again, a materials design project, which we have a very vast chemical space, and it's just impractical to think we could possibly screen and simulate all of those systems. So if we can start with a handful of molecules and we can use some of these active learning type approaches where they suggest the next sets of molecules to look at, I think that certainly is where a lot of this work is going. It's certainly where what we're looking at.
Thank you. That's really exciting, and also an interesting aspect that probably applies to many other AI projects that are trying to address the net zero transition. So I want to just give a last call for questions. So if anybody has a question, please type them into the chat now. Otherwise, we will bring the webinar to a close in a moment. In case anybody wants to ask something, please can you type that now? So if not, then I would just like to thank you very much again for your time today and for speaking to us and showing us some research results hot off the press. And I wish you good luck with the EcoAI project, Claire.
Thank you. Thanks very much.
Thank you very much. Lovely to see you.
Thank you.
Bye, everyone.